Ganges. Holy Mary, Mother of God, pray for us sinners now and at the hour of our death. Saint Thomas More,
Pray for us.
Pray
Pray for us.
So as you're probably aware, the worksheets are marked. There was a lot of work attached to this worksheet. It was out of 50. For the most part, it were done pretty well, although I think some people began with the right idea, but then the more of them they did, in some cases, the more corners ended up getting cut. The worksheet was intended to be repetitive. And by making you do it over and over and over again, as tedious as it might have seemed, it's a lot more likely you're going to be able to do it when you're under stress, when you're writing a test, because you're used to doing it. And that's why it's important that you don't develop bad habits early. So things like leaving units out, and a number of people did that. Some people decided that we'll just go with numbers and the magical units will show up at the end of them. That's not the way it works. Some people decided that they would change the sig figs. I'm pretty sure I said stick with the 2 decimal places for mass values. Some people decided to go with 1 or none at all. The last page that I made a point of saying is going to make a good test question. Some of them required names to be added, some of them formulas. Most people got the formulas, but some people forgot that some of them had, even though they have common names, there's a chemical name attached to it too. So for example, potash is potassium chloride, that type of thing. Milk of magnesia is magnesium hydroxide. And the other thing is if there's not room in the space available, and in a lot of cases there wasn't, I have to be able to read what you wrote. Some of you have really good little writing. Some of you, big or little, it's terrible. So when you're writing really tiny, it's very difficult to me to read what you wrote. Okay? But having said that, overall, I think the worksheets were done pretty well. If when you get your worksheet back, you're not sure if you can't understand my writing or whatever, maybe find me at a different time and I'd be happy to explain it to you. It's just that I kind of want to get a lot done today, so I'll hand these out and then we're going to go right into the next section, okay? Julian? I should probably do attendance while I'm doing this. How many people are going to be away again for whatever jazz, choir, band? Now, is that just Friday? Okay. You may want to get somebody to record the lecture, given that we're going to be doing some new stuff. But we'll see how far we get today. Daniel Cortina. Christina. Alexandria. Samantha. Olivia. Let me just sit there on the tea. Randall. Brienne.
Thank you.
Welcome, Leah. Daniel.
Thank you.
Julia. Sandra. Kayla. Diana.
Oh, you did it sheet by sheet. Oh, you did it fancy.
Annika.
Where did I go wrong? It's probably sig figs. I knew this.
Beckett. Samantha Long. Nicole.
Okay. So good so far. Oh,
Oh,
Ryan.
that's what he meant.
I did.
Allison,
Do not do it this way.
Claire,
Okay, my fault.
Some answers
and
missing.
Annabelle.
Oh, you. Oh, is that where I got my marks off?
That makes sense. Fair enough.
So we're all here. Awesome.
X.
I like how I highlighted it too.
You highlighted.
So, to start,
I just did the very last one wrong. Fair enough.
you recall at the end of section 3.4, I gave you a few problems to have a look at, a few review questions. Did any of them give you enough trouble upon checking your answers and not being able to explain why yours didn't match, that it's something we need to talk about? That's good news. Let us then move into 3.5. The warm-up that Gary gives you, I don't know that it qualifies as a warm-up. The idea behind a warm-up is you kind of bring information you already have to bear on a discussion we're about to have, to get you ready for what you're supposed to do. You guys have never heard of a mass spectrometer before. You certainly haven't had to analyze mass spectrometry data. So, I don't really know that it's gonna solve anything or serve a purpose to analyze that diagram. Maybe the business end of that is the very bottom couple lines underneath the warm-up, okay? So, we'll talk about the mass spectrometer in more detail when we get to chapter 5, but I think this is a big takeaway. The important point here is that one of the most sophisticated tools in the chemist's arsenal identifies compounds solely from their mass profile. In this section, you learn to determine a compound's formula from its composition by mass. Now, this sounds like a new topic, percent composition. Percentage composition is the percent of a compound's mass contributed by each type of atom in the compound, whether it's ionic or covalent. But if you guys can do molar mass, you can do this. It's that simple, really. Let's pick an example of, I don't know, something on your worksheet. So, how about marble or limestone, calcium carbonate, okay? So, remember page 1 of your worksheet would have gone in 1 mole of calcium carbonate. We have 1 mole of calcium. We have 1 mole of carbon. We have 3 moles of oxygen. Page 1. Page 2. In the periodic table, 40.07, I think.
0.08.
09. 08 grams of calcium per mole. 12.01 grams of carbon per mole, and 16.00 grams of oxygen per mole. Back to the worksheet, some people decided that because this was 16.00, they were safe to change it to 16. If you write 16, that means the 6 is a guess, okay? So the 2 zeros are kind of important, okay? So that means in every mole of this compound, 40.08 grams of it is calcium. 12.01 grams of it is carbon, and 48.00 grams of it is oxygen. If you can get this far, which I'm convinced you all can, you can get percent composition. When you add those things up, you get the molar mass. 100.09 grams of calcium carbonate per mole. Meaning every time you have a mole, you got that mass of the elements, or anytime you have 100.09 grams of it, that, and that fraction of 100.09 are those elements. Therefore, percent composition calcium equals 40.08 grams calcium divided by 100.09 grams of calcium carbonate. Anytime you have that mass of calcium carbonate, that fraction of it is calcium. If you multiply that by 100%, you get the percent composition of calcium. And this looks pretty close to 40% calcium, I think. I think that's right. Agreed? Percent composition by mass carbon is 12.01 grams of carbon divided by 100.09 grams of calcium carbonate times 100%. And that's awful close to that mass percentage carbon. Percent oxygen. Anytime you have 48 grams of oxygen in calcium carbonate, that's pretty close. I think it's like 47.96% oxygen. Okay? Now that adds to effectively 100%. Okay? The point being that if you have the chemical formula, you can get the percent composition by mass. And ideally, it should add to 100%, right? So if you can do this, which you already can, this is just the next step, right? What if the situation was reversed? What if you were told a compound was analyzed and found to contain 40.00% calcium, 12.00% carbon, 47.96, effectively 48% oxygen by mass? What's the formula? Now you just turn the arrows around. You go from percent to mass, mass to moles, moles to compound. And that's what we're going to do primarily in this section. Okay? Gary gives you an example of calculating molar mass, of percent composition, but you guys can do this already. You did sugar, sucrose, in your worksheet. In 1 mole of sucrose, I got 12 moles of carbon, which means I got 144 grams carbon. We don't need the stuff in the bottom here. In 1 mole of this, 12 moles of carbon times 12 grams per mole, 144 grams carbon. He's only taking it to 1 decimal. In 1 mole of glucose or sucrose, you got 22 moles of hydrogen, 22 grams. 1 mole of sucrose, you got 11 moles of oxygen, 176, it's a mole mass. Therefore, percent composition of carbon is 144 divided by 342 times 100%. This should be percent there. Okay? Percent composition by oxygen, mass of oxygen divided by the molar mass, and all these things add up to 100%. I don't know that you guys are learning anything new by doing any of these down here. Start with the molar mass and then go from there. The only one that's a little different maybe is number 3. Remember the worksheet where I told you, take the hydrogen and the oxygen apart? But in this scenario, you probably wouldn't want to, because his question is, calculate the percentage of water by mass. So you still have to calculate molar mass, but I would say, when you're doing this, in 1 mole of magnesium sulfate, you got 1 mole of magnesium, 1 mole of sulfur, 4 moles of oxygen, 7 moles of water. And it's, by leaving the water together, water has a molar mass of 18 grams per mole. So 7 times 18, what is that, 126 grams of the molar mass is water. And then you're just doing percent composition by water. But other than that, it's the same, okay? So molar mass naturally leads into percent composition. All you do is divide the mass of each element by the molar mass times 100%, okay? Did I go through that too fast, or does that make sense? Okay. So now let's talk about how we use molar mass to get empirical molecular, well, not structural, but empirical molecular. I don't really like the way he started this. Determining any chemical formula using the process we're going to describe begins with determining this. Every ionic compound has an empirical formula, and that's all. Because empirical just means whole number ratio. Empirical actually means derived from experimental data. But because the formula for every ionic compound is just a ratio, that's all we can do for ionic compounds, okay? If the compound's a molecular compound, then the empirical formula, which is just the smallest whole number ratio, isn't necessarily the molecular formula. Good example of that, let's say a question went something like, a compound is analyzed and found to contain this percent carbon, this percent oxygen, this percent hydrogen by mass. Calculate the empirical formula, and we'll do that. So let's say we were able, we haven't done it yet, but let's say you were able to determine the empirical formula of a covalent compound, and it ended up being this. That's the smallest ratio of the atoms in the molecule, okay? But as it turned out, the actual molecular formula wasn't this. The molecular formula was this. So when you determine the empirical formula, which has a 1 to 2 to 1 ratio, what extra bit of information would you need to know? Okay, that may be the empirical formula, but that's the actual number of atoms in the molecule. What extra bit of information would you need to know that it isn't this, but this?
You need a name?
Sorry?
You would need the name of it with the prefixes?
Well, if I told you it's glucose, does that tell you how many atoms of each in there unless you memorize it? Not really. So maybe it's better phrased as a two-part question. What extra bit of information would you need to confirm that it can't be this, but it actually is this? Because both of them have the same ratio. Loud. Molar mass. Precisely. Let's go to 1 decimal place. The molar mass of this compound, the empirical formula, and we would correctly label that as the empirical molar mass, would be 12.0 plus 2.0 plus 16.0, right? So the empirical molar mass of that formula is 30 grams per mole. Agreed? You did the same thing here, it would be 180 grams per mole. So how do you get from here to here? Divide this by this. Divide the actual molar mass by the empirical molar mass, and you'll get a multiplier. It has to be a whole number. Which means even though the ratio is 1 to 2 to 1, the actual formula is C6H12. Okay? Now there is a molecule, CH2O, but it isn't glucose. It's formaldehyde. We use it to preserve laboratory specimens, embalming fluid. Okay? We put that on dead bodies. A mouthful of that will kill you. Your brain runs on this, yet they have the same empirical formula. Now Gary adds a third thing here, structural formula. That's beyond what we know about yet in grade 11 chem. This has to do with the actual connectivities of the atoms. And one of the intriguing aspects of organic chemistry, which is what this is just because you know the actual molecular formula tells you very little about the actual structure of the compound. Even this, knowing it's glucose, there's actually two forms of glucose. One of them's a straight chain of 6 carbons, one of them's a ring, but they're both glucose, and they both have the same formula. Maybe a simple way to represent the difference between molecular and structural is if you go back to the warm-up, what compound did Gary analyze in that mass spectrometer? What's the name of the compound in the warm-up? Pentane, right? Pentane has the molecular formula C5H12. Notice it's CnH2n plus 2. But just because it's C5H12 doesn't mean it's pentane. This is pentane. Every carbon is stuck to 4 other atoms. Every hydrogen is stuck to only 1 atom, because hydrogen can only form 1 bond. So that's pentane. Notice we've got 5 carbons in a chain. But there's more ways to connect 5 carbons and 12 hydrogens than that. Notice there's the CnH2n plus 2. Another way that that molecule can exist, or that formula can exist, would be this. It's still got 12 hydrogens, it's still got 5 carbons, but now there's no 5 carbon chain. There's only a 4 carbon chain. Whether you go 1, 2, 3, 4, 1, 2, 3, 4. There's still only 4 carbons in the chain. That isn't pentane, but it is C5H12. We call this methyl butane. And there's another way. This is also C5H12, but it's neither pentane nor methyl butane. It's called dimethyl propane. And now, no matter how you count it, the longest carbon chain is only 3. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. They're all completely different compounds. We call them structural isomers, and Gary alludes to that in the down here. Different forms of the same all the same chemical formula with different connectivities of atoms. As the number of carbons, and these are the simplest types of organic compounds, they're called hydrocarbons. As the number of carbons increases, the number of isomers goes up geometrically into the millions or billions. And it's one of the unique things of carbon. Okay? And we'll look at another example of that later. You won't have to do this. Okay? From here to here, fine, but here to here, no. And if all I knew about a compound was it had the molecular formula C5H12, I don't know what the compound is. It could be pentane, but it could also be methylbutane, it could also be dimethylpropane. And they're all different molecules, different properties, different reactivities, right? But let's start at the beginning. Let's start with determining empirical formulas. There are 3 steps to determining an empirical formula. Write this down. Steps to determining an empirical formula. Or steps to determine an empirical formula. And that just means the smallest ratio of atoms in the compound. First step, the mass amounts of each element. The mass amounts of each element in the compound are given or determined. The mass amounts of each element in the compound are given or determined. That's step 1. Mass amounts of each element in the compound are given or determined. Step 2. The mass amounts of each element in the compound are converted to the mole amounts of each element. The mass amounts of each element in the compound are converted to the mole amounts of each element. And step 3. The mole amounts of each element in the compound are converted to the smallest integral ratio of elements. The mole amounts of each element in the compound are converted to the smallest integral or whole number ratio of elements. So we go from a mass to a mole to the smallest ratio. And let's I guess we can have a quick look at the quick check, just the difference here. Here's the structural formula of acetic acid. There's the structural formula of oxalic acid. That's my vinegar sour, that's rhubarb. Yes?
Can you repeat step 3, please?
The mole amounts of each element in the compound are converted to the smallest integral ratio of elements in the compound. So that's acetic acid, that's oxalic acid, that's my rhubarb sour. The molecular formula, you could write it C2H4O2. Although it's often not written like that, but that is the molecular formula. 2 carbons, 4 hydrogens, 2 oxygens. The empirical formula is the same as the empirical formula for formaldehyde or glucose. Okay? Here, the molecular formula C2, but instead of H4, it's H2, and instead of O2, it's O4. So the empirical formula would be CaO2. Okay? And notice that each of these has a COOH. So the more common way to write acetic acid is this. And oxalic acid, you could, although it's not written this way too often, could write it like that. Okay? But you guys know it as HC2O4. H2C2O4. I've written the carbon first here, but that's often how it's written, H2C2O4. So, let's now determine an empirical formula. And we're gonna do it from percent composition. So let's look at Gary's sample problem here. Determine the empirical formula of a compound that is found to contain 48.65% carbon, 8.11% hydrogen, and 43.24% oxygen by mass. What does percent mean? Per what? Per
100.
100. So if you're given percent composition by mass, start by writing in 100 grams. If that's what percent means. If that's the percent carbon by mass, that means every time you have 100 grams of this compound, 48.65 grams of it has to be carbon. 8.11 grams has to be hydrogen, and 43.24 grams has to be oxygen. That's what percent means. So step one, the mass amounts are given or determined. You determine it. Because you said, well, at every 100 grams, I got that mass of each element. Step two, the mass amounts are converted to mole amounts. Now Gary uses only one decimal place. We'll go to 2. But I'm glad he introduced this in the sample problem. Notice we've got 3 sig figs here, 4 there, 5 there. Carry at least 1 extra sig fig through. Don't round. The more sig figs you carry through, the better the formula that you're looking for will show up when you go through the 3 steps. Okay? So we're going to convert these to mole amounts. According to the periodic table, a mole of carbon, we're going to 2 decimal places, it's 12 grams. A mole of hydrogen is 1.01 grams. And a mole of oxygen is 16.00. But it cancels. And again, we're carrying, we're going to put 5 sig figs here. So 4.0542 moles carbon, 8.1100 moles hydrogen, and 2.7025 moles oxygen. Now, I don't like what Gary does after this. I don't like doing it this way. All the units magically disappear. Don't do that. So there's step 1, mass amounts were determined. Step 2, mass amounts were converted to mole amounts. Step 3, we're going to convert the mole amounts of each element to the smallest whole number ratio of elements. To do that, we divide all of those mole amounts by the smallest number. Okay? So we're going to divide them all by 2.7025. So now we're going to get mole amounts from which we get a whole number ratio. So this is obviously 1.000. Let's go with an extra sig fig. Moles oxygen. So you guys get your calculator. What do I have? We can probably go with 40. What's that divided by that? What's 8.1100 divided by 2.7025? And notice we're keeping moles. Feel free to punch the buttons in your calculator.
2.997.
6 point?
2 point.
2.997?
Yeah. Oh wait, no, that was for hydrogen. Sorry.
Okay, this one.
Yeah, that was.
It's not, is it 2 point? 2.997?
Or sorry, I thought that was a 1. Is that an 8?
It is 8.11.
Oh, 1 1. Yeah.
Yeah, I'm taking it off of there, 8.1100.
Never mind. It's just 3.000.
And how many moles of carbon? 4.052 divided by 2.7025. That's not a whole number, is it? What is it? 1.4993?
Yeah.
Okay. Now, with this level of precision, we're not justified in rounding that down to 1. Okay, because where the guesses aren't anywhere near that. So this is effectively C 1.5 H3O1, correct? To turn it into whole numbers, we gotta multiply through by 2.
Oh yeah, it's like last year.
In every 100 grams of the compound, we have 1.5 moles of carbon, 3 moles of hydrogen, 1 mole of oxygen. But we can't round that to 2 because that's not a guess. The guessing starts way over here. So this becomes C3H6O2. Okay? If you decide that you're gonna round that up, you're saying that that 5 is a guess, which it clearly is not. That's why we carry all those sig figs through. So that's the empirical formula for this compound. Smallest whole number ratio. Now, that might not be the molecular formula, but it's the empirical formula. Does that process make sense? Now look at how this is opposite to what you guys did in the worksheet. You started with a formula, and you would have said, in 1 mole of this, I got 3 moles of carbon, 6 moles of hydrogen, 2 moles of oxygen. Convert those to grams, you would have got here. And then from there, you got the molar mass, right? So we're going in exactly the opposite direction. Exactly the opposite of what's the percent composition by mass of this compound. You start with the percent composition and you go that way. So all we're doing is turning the arrows around. Look at number 1. Usually you write the formula in the same order the elements are given in the question. So if this formula starts with lithium, it has to be an ionic compound. Alkali metals are never involved in covalent compounds. And if it's an ionic compound, that's the only thing we can write. There's no such thing as a molecular formula for an ionic compound. My point is, if you do this correctly and you get the correct empirical formula, you should be able to recognize it and actually name the compound. In other words, it should make sense based on the smallest ratio, because that's all you can do for an ionic compound. So try number 1. Start with that, because we're given percent composition by mass. Now Gary gives you the 1 decimal place. Again, use 2 decimal places from your periodic table. Carry an extra sig fig through in your steps, and then the correct formula should be pretty clear when you're finished. looks just like water, doesn't it? It's not. All of these little things. But you can't see them. Because they've got the same refractive index as water. The compound is similar to what you put in disposable diapers, sodium polyacrylate. If I drain all the water out,
It's like invisible pumper. That's so freaky.
there's remnants from the open house last night. There's a little kid, looks like he was in like grade 2 or 3, and he started putting one in his mouth. Mom got a little worried. 99.999% water. They start out about as big as the head of a pin, and they just absorb water. But because they're just effectively water, they refract light in exactly the same way as water, which means you can't see them in the water. I digress. So 100 grams of that compound, 18.7 grams of lithium, 16.3 grams is carbon.
Oh, it's not supposed to get bigger. I have to divide. Oops.
5 grams is oxygen. Step 2, convert to mole amounts. 1 mole of lithium is 6.94 grams. 1 mole of carbon, 12.01 grams. 1 mole of oxygen, 16.00 grams. And chemicals. How many moles of lithium do you have? Give me 4 sulfates. What's 18.7 divided by 6.94?
Oh, he wants 4.
Anybody?
2.6945.
2 point?
6945.
2.695 moles.
If he wants 5, what the
How many moles carbon? 16.3 divided by 12.01.
1.357.
doesn't matter. I don't know.
And that's gonna be 4.1. 65.5 divided by 16.
4.093.
0.93.
9.4.
So that's step 2. Divide all of them by the smallest value.
Oh shit.
How many moles lithium? Pretty close to 2, right? 1.9 what?
6.
985?
6.
Everybody agree with that? 9857?
6.
So let's go 1.986 maybe. And this is pretty close to 3, isn't it? Feel free to use your own calculator like you will on a test, you guys. 4.093 divided by 1.357.
7.
decimal place that we began with. This is legitimately rounded to that, is it not? Does that formula make sense? Yeah, because carbonate's 2 minus, lithium's 1 plus. Right? Now, that's all we can write for this compound because it's ionic, and the formula's just a ratio. There's no molecule to worry about. Number 2 is exactly the same. You begin with in 100 grams. For number 3, you don't have to do that because the mass amounts are given directly. Notice we're starting with silver, so this is going to be an ionic compound. And then we have sulfur and oxygen. So this might be silver with either sulfate or sulfite as a polyatomic anode. But I don't know yet. Now if it's SO3 or SO4, each of those have a 2 minus charge. Silver's only 1 plus. But again, the mass amounts are given. So you don't have to say in 100 grams. You already know what the masses are. Convert mass amounts to mole amounts to smallest whole number ratio, and you're going to get Ag2SO something, either SO3 or SO4. But just like lithium carbonate, you should be able to look at it and go, yeah, that makes sense in terms of what I know about silver's charge and what I know about polyatomic anodes. Okay? This is all about empirical formulas. If it's a molecular formula you're determining, then you're going to need molar mass as an extra bit of info. Gary uses the example here of butane. If we worked out the empirical formula of butane, it would be C2H5. Now, that would have come from an empirical formula C1H2.5, which means we have to multiply everything by 2 to get a whole number. That formula has an empirical molar mass of 29 grams per mole. But then he told you, well, the actual molar mass is 58 grams per mole. That divided by that has to be a whole number. So he says here, a compound's molecular formula is an integral multiple of its empirical formula. And if when you're doing a question like this and you get what you think is the correct empirical formula, but then you divide that mass into the actual molar mass and you don't get a whole number, let's say you get something weird like 2.49 or 2.37, it's wrong. At that point, it has to be a whole number, okay? A compound has an empirical formula of CH2. The actual molar mass is 42 grams per mole. What's the molecular formula? Well, go to the empirical formula and determine the molar mass. We call that the empirical molar mass. In 1 mole of this, I'd have 12 grams of carbon, 2 grams of hydrogen, leading to an empirical molar mass of 14 grams per mole. But Gary tells us the actual molar mass is 42. So the actual molar mass divided by the empirical molar mass should give a whole number. Okay? Now, I don't really like the way he's done that. I prefer you to write this times 3 gives C2 or C3H6. So by doing this, you're getting the multiplier. That is what you have to multiply the empirical formula by to get the actual molecular formula. But just like our example we started the class with pentane, that does not tell you how the atoms are stuck together. And you might think, well, how many ways could you stick 3 carbons and 6 hydrogens together? Well, there's 2. One of them looks like this. notice that in this version of C3H6, every carbon has 4 bonds, every hydrogen has 1, which will always be the case in hydrocarbons. The other way would be this. Not only does carbon happily form chains of any length with itself, and it's the only element that does that, but it also happily forms rings of any size. This is called cyclopropane. That's called propene. No rings here, but a double bond. No double bond, but a ring. And if we ever get to organic chem, depending on the number of advisories we have to endure, we're going to learn that anytime you see a formula CnH2n, it means either there's 1 double bond or there's 1 ring. Okay? But we'll get there eventually, maybe in May. Now, if you look at the practice problems, Gary does the first 2 for you, effectively. He gives you the empirical formula. But you knowing me as well as you now do, I would never do that. A compound has an empirical formula C3H4. Which are the possible molar masses of the compound? Well, it has to be either that empirical molar mass or a whole number multiple of it, correct? The actual molar mass can't be less than the empirical molar mass. That doesn't make any sense. What would be the empirical molar mass of that compound? Well, 3 times 12 is 36, plus 4 is 42, correct? You guys see that? So could the molar mass possibly be 20? No. Could it be 55? 3 times 12 is 36, plus 4 is 40, right? So could it be 55? Cool, because that divided by 40 is not a whole number. Could it be 80? Yeah. Could it be 120? Yeah. But not that, because that's a fraction, and not less than, because that's absurd. What about number 3? He doesn't do that one for you. A question like this isn't a bad test question, isn't it? I would probably word this in a 2-part question. I go, a compound is analyzed and found to contain that mass of carbon, that mass of hydrogen, that mass of oxygen. A, determine its empirical formula. B, the molar mass of the compound is 62 grams per mole. That's the molecular formula. And notice that one question kind of encompasses the whole section. Because if you turn the page, the section's done. Now, I'm not saying that you guys have to be an expert at this already, but how about for Friday, which as far as or Thursday, which as far as I know, is a full day. I think originally there was supposed to be a staff meeting, but not. So try the last couple practice problems for empirical formulas. We did the lithium carbonate, but there's a couple more. And try maybe 3 in these set of practice problems. And then we'll pick maybe 1 or 2 from the review on Thursday. Oh, sorry, Friday, because today is Wednesday. And then that'll be it for 3-5. We still have another section to do, and that's brand new stuff. That's solution chemistry, that's molarity. So we'll start that on Friday. We won't get finished at them. After Friday, we meet Tuesday and Thursday, right? Tuesday, I think, is a full block. Thursday obviously is not. But we can at least get a chunk of 3.6 done. And for the first time, when we get to 3.6, you're gonna see an insert that I added on page 147 to 149. The other thing that's gonna take us a little time in section 3.6 is we're gonna transition into chapter 7 briefly, because we're gonna talk about dilution chemistry. And dilution chemistry is really the reason I put that insert in there. Because Gary's wheel models don't work for dilution chemistry, but a graphical way to approach it does. So, again, it's gonna take us a while. There's no chance, obviously, that the test will be before Christmas break, and there's no chance that it'll be immediately after Christmas break. So I'm not gonna say, now we're done 3.6, good luck, first day back, we have a test. I'm not gonna do that. I suspect the amount of Christmas presents I would get would go down dramatically if I did that to you. Okay? Which, not that it's a motivation at all, but just saying. So how about for next time, you guys complete those last couple sets of practice problems, and then we'll do maybe a few review questions, and then we'll move right into 3.6. As you're probably aware, this chapter test is going to be a little bigger and perhaps a little more challenging than the first couple you wrote. So I will, because this is such a pivotal topic and because it's rather big, I'll try to be a little more specific in terms of what I want you to focus on, at least for the written response section of the test. I won't be able to ask you everything we did in 6 sections, because we only have one period when we do end up having a test. So I'll sort of suggest what to focus on. So I just said one of them, an empirical and molecular formula determination. You don't have to do that. You also remember in the mole worksheet, that last page. And just those 2 things take care of a lot of stuff in chapter 3, okay? But we'll also go into solution chemistry. And section 3.6 is the other volume point on the rim of the wheel. Because we talked about molar volume, but we're also going to do volume of a solution. And then that's molarity. But I don't want to start that yet, okay? And I'll see you guys Friday, and how many people, once again, will not be here Friday? Hands up. So, you would agree if you weren't here today, you would have missed some stuff? So, maybe suck up to someone who you think will be judicious in not only recording the lecture, but even maybe taking good notes, in the event that they want to sell them to you upon your return to class. Yeah.
How about free?
And I don't know that your choir director is going to be able to help you with your camp. But I am going to continue teaching, so. Yeah. Yep.
Can I hold one of those?
You can have one.
I can have
Just
one.
don't eat it, okay?
Put it in your mouth.
Yeah.
Ew.
I'll take one here. Free of charge.
Oh, ew, bro.
What the? Why is it so like?
Yeah, grab one. Don't eat it.
Afternoon, staff and students. The winners of the raffle today are Laura in grade 10 and Cecilia in grade 8. Please come to the front office to collect your prize. Now, as a faith and learning community, let us prepare ourselves for the end of day prayer. In the name of the Father, the Son, and the Holy Spirit. Dear Lord, help us accept the difficulties and partings we face in our lives. Grant us the faith and grace to be able to let go of all that we have, so that one day we may be at peace with you. Help each of us to be your instruments and continue the great works you've begun. May we all accept this responsibility in order to build your kingdom here on earth. Amen. St. Thomas More, Blessed Edmund Rice,